Yeah, and I'm going to be sharing some thoughts and results of our work on document information extraction. Now, some quick facts about SAP. For those of you who may not know it, SAP has more than 100,000 employees in more than 180 countries. We have more than 440,000 customers in 25 and plus industries. Last year's revenue was around 28 billion euros, of which 4.2 billion were spent in research and development. My team is part of so-called AI business services. SAP AI business services is producing reusable services which make use of artificial intelligence to solve all kinds of business problems. These services are easy to consume. That's the idea, via some REST APIs, and they're supposed to extend business processes or applications. Now, we have a couple of business services already developed, such as, for instance, service ticket intelligence, document classification, business entity recognition, data attribute recommendation. One specific service I want to talk about today, and that's document information extraction. So the idea is that we automatically extract information from unstructured documents. And this directly brings us to the problem description. So we have some kind of document, in this case an invoice, a PDF of it, some image, and we would like to extract information from that. For instance, invoice number, invoice amount, and also parsing the table. Now, one can roughly decompose the problem in two separate types of fields. The first set of fields are the so-called header fields, which are highlighted in red boxes here. Those are, for instance, the vendor name, vendor address, or also the total amount. These fields are usually unique to the document. And then we, of course, also want to parse the table. And the table, is usually comprised, of course, of columns and so-called line items. This table looks fairly simple. It's fairly structured, but there are horrible-looking tables occurring as well. That directly brings us to the challenge. We want to be able to parse and read out information from a large variety of different document layouts, in this particular case, invoices. We would like to handle multiple languages. We would like to parse the tables, and generally the document exhibits some two-dimensional structure and layout, which at some points could be fairly complicated. Just to give you an idea of how diverse the data that we're working with is, on the left-hand side, you see the vendor distribution in our data set. And essentially, this plot tells you that most documents are from a vendor that occurs only once in this data set. So if you take a vendor, each vendor has maybe a unique template, then this roughly approximates the number of unique templates in the data set. Also, we have a fairly diverse distribution of languages. These are just the dominant ones, but there are even also multiple others. And also, just to give you an idea of the distribution of the fields, where they can occur on the document page. So on the left-hand side, you see, for instance, the spatial distribution or the location of occurrence in our data set, where the total amount can occur on the invoice. Naturally, it's clustered towards the bottom right corner, but it seems to pretty much occur everywhere on the page otherwise. Likewise, the line item, the quantity line item field is also located throughout the page. There also seem to be certain clusters, but it seems to also be, that's not hard-coded to it. Now, our data set that we have is comprised of 10,000 training samples, around 1,000 samples in the validation set, and another 1,000 in the test set. And our ground truth that we collected is in the form of bounding box annotation. And the bounding boxes basically indicate the region of the document on the page where the given value for a given field is located. So, for instance, the orange box surrounding ABC communication, that's the value that's locating the value of the vendor for this document in this case. Now let's have a look at the various different approaches. So one can start, as input, one receives this PDF document or an image of the document, and then the first obvious step is to run it through some optical character recognition software. And that obviously gives you the string, the text information of the textual content of the document. It also gives you the word boxes. So for each word on the document, you also receive a bounding box from the optical character recognition engine. And this, combined with our bounding box annotation that we have in our data set, we can actually know for each character in the input the class label that we have. Now, the first obvious approach that one can take is to just take the serialized text together with the labels and just formulate the problem for extracting information as a sequence tagging problem. So sequence tagging is as simple as this. So you receive some input string. In this case, John Smith works at SAP since blah, blah, blah. And then your network, which in this case could be a recurrent neural network or a convolutional neural network or a transformer network, would then for each character or for each word or for each word piece output a class. Now this works, but it has problems because if you look at documents that we're looking at, especially invoices, you usually have some layout structure. And depending on the serialization that you have with your text, you may break certain relationships in the text that are important, or certain layout information that is important. So, for instance, in this case, ABC, the entire address box and with the vendor of that vendor is mixed up with the information about the invoice number and invoice date on the right-hand side. And this, of course, makes it extremely hard for a sequential model to disentangle these pieces of information. This problem is even more pronounced when parsing tables, where in this case, for instance, the line item description field is mixed up with the neighboring columns. And then, of course, it becomes really terrible for the sequential model to disentangle the words in the classes. Well, you can also formulate this, of course, as a computer vision problem. So instead of working on the text, one can just directly work on the document image. So going directly from the pixel level all the way to predicted bounding boxes in this case. However, this is more costly and more problematic than one may think because, first of all, it's computationally very expensive. You need to have a relatively high resolution in order to resolve small fonts. And then also you need to go end to end. You need to go from the pixel level all the way to the prediction. And essentially the system or the model that one wants to train would need to first interpret characters and words from the pixel level. And that's where our idea comes into play, the so-called character grid representation. Feel free to also check out the paper that we submitted to EMNLP some time ago with much more details. So the idea is as follows. So you have some string on the document page. In this case, you have SAP SE, those two words. The OCR engine returns the string to you, but it also gives you the bounding box of the word. And you can split up the bounding box into character boxes, and then for each character you can map to the same constant index, depending on your vocabulary. So you may build up a vocabulary of known characters, and the letter A, for instance, or the character A will always be mapped to 0, and so on and so forth. Now the idea is that each pixel inside a given character box is basically mapped to the same constant index of the vocabulary index for that character. And in practice, for an entire document, this looks like this. On the left-hand side, you see the raw document image, and on the right-hand side, you see the so-called character grid representation. Now, the character grid representation is a rank 3 tensor. It has a certain width and a certain height, reflecting the size and shape of the document page. And it also has some certain embedding dimension. In case one is encoding characters, one would most likely select a one-hot encoding embedding. The advantage now of this representation is that that one already directly captures textual information. The two-dimensional relationship of the text and the layout is preserved, which is important. And also we can aggressively downsample because in order to have knowledge about a certain character on the document, all that's necessary is a single character pixel. And usually character on the document image level, you would need to have at least, let's say, 10 by 10 pixels in order to be able to resolve a certain character and really tell apart a character from another. And then we formulate this in terms of a semantic instance segmentation task that is also commonly used in computer vision. So instead of using the image as input, we use the character grid representation. We pass it through some fully convolutional neural network encoder, encoder subnetwork, and then we have two decoder branches. One decoder branch is creating a semantic segmentation mask. That means for each pixel in the character grid input, we produce a class. So we can classify each character pixel according to its class. So for instance, whether a certain character pixel belongs to the vendor name or to the invoice date, and so on and so forth. And then with the bounding box regression, we can tell apart different instances of the same class. In our case, we like to use bounding boxes to group line items and to tell apart different line items. And this is how it looks like. Again, on the left-hand side, you see the original document. In the middle panel, you see the character grid representation. And on the right-hand side, you see the prediction. You see the segmentation mask, and on top, you can see those blue bounding boxes, which denote the line items. Now, this information combined, so this geometric information, the semantic segmentation mask and the bounding boxes are geometric information. This combined with the output from the optical character recognition engine, which also gave you the bounding boxes and the position information of each word. If one overlaps these two pieces of information, one can actually determine the text that belongs to a certain field. And so at the end of the day, you receive as output maybe a JSON file or some dictionary of key value pairs. Now, a valid question is, how can we do better? And one thing that we did in order to improve this is to use word vectors on one hand, and then on top, also incorporate contextualization. Now, word vectors, very similar to the character grid representation, we can also create a so-called word grid. And the advantage for such a word grid may obviously be that, first of all, you don't need to learn words from the characters first in order to determine the semantic meaning. And on top, you can also leverage pre-trained word vectors, which may have been obtained via some pre-training step. So Word2Vec or GloVe, which was trained on some external, much bigger corpus than what we have at our disposal for our invoices. However, the disadvantages of the word grid is most certainly that you can't handle easily all the vocabulary words. They're not covered. The word which is not in the vocabulary can't be read. And also it's not useful for words such as an invoice number. So we expect, especially in invoices or certain business documents, a lot of weird strings which don't even resemble words. Now, another thing that is really helpful is contextualization. If you look at the following example, you see that the word may, depending on the context, has a different meaning. Now, if you just take static word vectors and disregard the context, then you would cast or you would map the word may in both contexts to exactly the same word vector, which would be incorrect because really these are have two different meanings in this case. So the embedding vector that one is using should be different and really context depending. And this idea was brought forward also already in 2018 by Peters with this ELMO idea, the ELMO network. Now, very roughly how this works. So the idea is that you have a language model some neural network, which is trained to predict the next word in a sequence for autoregressive networks, or if you use denoising autoencoder type of models such as BERT, predicting the missing words in the input. And these language models, as a result, produce or can produce feature vectors for each word depending on the context. And these feature vectors, they can be produced by just looking at the activations in the different layers, taking a convex combination of them, or just looking at the last layer, and so on and so forth. So multiple different options. A nice aspect of these language models on top is that you can actually pre-train them with large amounts of unlabeled data. And in our case, this is helpful because we happen to have a large pool of unlabeled invoices at our disposal. Now, just the way it works in a sequential way, this is done sequentially. You can also do it in 2D and construct something that we call BERT grid. So the idea is that we have some spatially arranged text, and then for each text element, or for each cell in this case, we would like to create an embedding vector which is context dependent. And these embedding vectors, this embedding function, is basically obtained via a pre-trained BERT language model that was trained on invoices, on a large set of unlabeled invoices. Now, in practice, the pipeline looks such. So you have as an input the raw two-dimensional document. So you have the document image. Then you run OCR over it. This produces a set called D. D is basically comprised of the different words and characters plus their bounding boxes. Now then we serialize the text inside D to produce a serialized version of that same text called S. And this is passed through the BERT language model. And from there, we produce these context vectors. And then we bring them back to the original set D by looking also at the bounding box location of a given word. And then, just like what we did with characters, where we filled each pixel which belongs to a certain character inside a given character box, we would know, instead of filling it with a constant index or a constant one-hot encoding vector, we would now fill it with the appropriate embedding vector coming from, or contextualized vector coming from the language model, from the BERT language model. And then we just proceed as before. We pass it on through the neural network all the way to the downstream task, in our case, information extraction. Now, one can, of course, also fuse all these different representations. So the character grid, the word grid representation, and the BERT grid representation we can fuse. It makes most sense to couple the character grid representation with either the word grid or the BERT grid, but not all the three. But this is how it looks like in practice. So our neural network that we have seen before, which was comprised of this encoder and the two decoders. The encoder was comprised of multiple convolutional blocks, and in our case, we just replicate the first convolutional block. One convolutional block is working on the character grid representation as input, and the other one the BERT grid representation. And then they're being fused, in this case just added, and then from there the encoder is just one stream which is passed onto the decoder. And that already brings me to the results. If you look at first quickly explain the metric. So what we're measuring here is essentially the amount of human effort that is necessary in order to fix the model. The higher the number, the better. The less fixing is necessary. And we count it such that for each ground truth element in our data set, for each field, we count the number of modifications that we needed to do. Likewise, the number of additions and the number of deletions that we need to do. As soon as a single character in our prediction is incorrect, we deem the extraction already as a failure. And this creates essentially for our metric somehow a lower bound. So it's more restrictive than maybe necessary, especially for those fields where you have lots of characters and lots of descriptive text, like a line item description, for instance. It's easy that a single character may be incorrect. And then we, in our case, count the entire field to be incorrect. But that's fine. I mean, it's better to be conservative compared to be overly optimistic. And then you see here in the table actually the different versions of our models, and then with the various different columns you see a number of representative fields. Those are not all fields. We have way more fields that we extract, but just some representative numbers so that one can easily present them on a slide deck. What can be seen is that the character grid representation, which is used as a baseline, is essentially giving for lots of fields already an acceptable performance, but in this case, it's performing the worst compared to everything else. Well, actually, the pure word grid representation is actually performing worst, which is not too surprising because we have many out of vocabulary words, and in this case, I would expect that actually plain character grid representation works better. That was actually also, by the way, the reason we started out with the character grid representation right from the beginning. But if you merge the character grid and the word grid representation, then you already get better. If you just take the plain word grid representation, which is using the language model and the contextualized vectors instead of just one-hot encoding vectors or static word vectors, it's already making a massive jump forward. And then if you combine this even with character grid representation on top of character level information, you can even squeeze out further accuracy. Yeah, also feel free to look at our paper from last year in Europe for a couple of more details. Just very quickly at the very end, these are just example outputs that you see here. It is on the top row, you see example inputs, the character grid representations for a bunch of documents, and below that you see the predictions. And this is just to highlight a little bit the variety in terms of layouts that one can have. Maybe let me skip this one and maybe directly go to the conclusions and say, because I think I'm over time, I don't know if, how much time is left.
None, but it was very interesting.
Okay, yeah, so let's leave it at that, and thanks.
Okay, thank you, Christian, for the presentation. Very interesting. As a quick side note, I think I did this also 4 years ago in a previous job, and I remember all the approaches here, so it's very similar, really cool. But it was the time before BERT. I have a question. How robust is your model for different languages? Because this, I remember, as one of the biggest issues we had 4 years ago, especially trying, the second generation of the BERT model and so on, because there was usually only data for English available and not for German and other languages. What is your finding on the multi-language problem?
Yeah, good question. I mean, you've seen that the data set that this is based on is a bias in terms of English. So naturally, it can handle English much better. But we've done all kinds of tests, and by now we have collected much more data on top, also for different languages. And typically, we find that actually having a mixed model can have an advantage, especially for those languages which are a little bit underrepresented, because the layout information is actually always the same, unless you have a really weird language with a completely different layout. But let's say the Latin languages all share commonalities, which make it plausible to put all the languages in just one big bucket when training and testing. But of course, one has to be a little bit careful, especially when using word vectors, that one needs to obviously word vectors oftentimes are locked to a certain language, and so you need to do something that is not is agnostic to the language. And that's actually also, by the way, a reason why we started out with the character grid representation and focused on characters first.
Okay, thank you.
Georg, just quick question from my side. So what's the state of availability of this work to, let's say, SAP customers, and how do you actually make this available? Is this something that is kind of already part of the SAP suite in some way, or what's the plan there?
Yeah, this model is in production. And the character grid model is already in production, I think more than 2 years by now. Yeah, of course, we also have some improvements which also made it to production. Already we're now supporting more document types, more languages. And yeah, if you're using the SAP Document Information Extraction Service docs, then you're essentially using large bulk this model.
Okay, thank you. Do we have any questions from the community here?
And if so, please type them into the Slido. The link is also in the chat on top, so we can pick them up here. Also, if you happen to want to have a conversation with Christian after the main stage, we have sessions prepared for every speaker, and then Christian is in one of those sessions, and so you can have actually a direct conversation with Christian as well, if you have any questions on this one that go deeper or come later.
Cool. Okay.
Super helpful. I'm always surprised by the level of technical details when we're having a kind of a Leipzig event, which is great. I really like to go into the details, and that's super helpful. Also, the pipeline that you described makes a lot of sense. Thanks.
The blue-collar workers of AI, Yuri.
Yeah.
But to me, that's also the fun part.
Yeah, indeed. Okay.
And there's, before we switch over, there's one question.
Cool.
A question, please. Which aspects should be taken into account in production, as the model don't have yet 100% accuracy?
Yeah, good question. I mean, oftentimes what happens is that one way of addressing this is to have humans in the loop. To have a certain, for instance, a service center of accountants which fix the model predictions. Or alternatively, we just live with the finite accuracy. Some fields, the numbers that I present seem very conservative, very pessimistic, let's say. In reality, it's not as pessimistic. The model is performing better, also because in our test set we deliberately put documents which are not part of the training set, just to test the generalization capabilities. In practice, if you have a certain customer, then you may want to have the document templates that a certain customers may be seeing also as part of the training set, obviously, so that you can squeeze out extra accuracy there. Yeah, but a plausible approach is to actually have humans fix the model prediction.
Makes sense. Cool. I think with that, I would say thanks so much, Christian.